Today I'm talking about augmenting physics education with haptic and visual feedback. Let's start with some general backgrounds. Haptic simply refers to anything related to the sense of touch. This includes our perception of temperature, texture, and in particular relevance to this study, our perception of forces and force feedback. Haptic feedback is used in educational settings in many different fields, most of which are very specific and specialized. For instance, haptic feedback is used in cockpit simulation to add realism to the experience of pilots. Haptically enabled simulation is able to better capture routine and emergency situations with higher realism. Furthermore, surgical simulations also benefit from haptic feedback functions, which not only allow upcoming surgeons to practice simple procedures, but also allow practice run of complex procedures for trained surgeons. However, the development of haptic feedback in physics education remains under study. The nature of physics education includes abstract and unintuitive concepts like forces and frictions, and even though these concepts are tangible phenomena in real life, in classroom settings, they are often presented through a pen and paper approach. For instance, forces are presented as arrows of different directions and magnitude, which can be less intuitive, especially in an elementary classroom. This brings us to our target population. While we hope for the finding of this study to trickle down to elementary classrooms, we do not intend for haptically enabled simulation to be directly deployed in such classroom, nor is our target population elementary school students. Instead, we aim to educate the educators. Physics is often absent from elementary science, not only because of its abstract nature, but also because teachers lack a tangible way to present it. Therefore, through haptic feedbacks, we hope to present more tangible ways to describe physics concepts and, by extension, introduce more physics education in elementary classrooms. The main apparatus used in the present study is the Novin Falcon haptic device, which is able to both perceive and produce three-dimensional force feedback. This is categorically different from the experience with a mouse or a touchpad, which is two-dimensional in nature. The current deployment of the Falcon is mostly in the gaming industry, where different modules can be switched on to allow a real-time interactive experience with simulations or programs. In the current study, we intend to explore deploying haptic feedback in a buoyancy simulation with the hope of examining if haptic feedback will improve learning outcome. I want to briefly clarify with the definition of buoyancy. Buoyancy simply refers to the ability or tendency of an object to float in water or air, and buoyant force refers to the upward force that is placed onto an object when submerged in such fluid. There are several foundations of our hypothesis. Firstly, we expect haptic components in the simulation to improve learning outcome because it adds realism as well as allow hands-on experiences. Furthermore, we expect visual feedback to improve learning outcome because it is more similar to the traditional classroom experience and therefore is more familiar for the participants. And lastly, we expect that the two components to interact and produce a better outcome than deploying alone. Therefore, we hypothesize that using the simulation system will improve buoyancy understanding than without, that enabling the visual feedback components will yield better understanding than not enabling, and that enabling haptic feedback components will yield better understanding than not enabling. Also, we hypothesize that the combination of haptic and visual feedback will yield better understanding than any single conditions. We use the 2x2 between subjects design, where a participant is randomly assigned to one of four conditions: control, visual only, haptic only, or haptic and visual. Participants' performance is evaluated by two buoyancy tests given before and after the simulation, and participants' score in the pre-test and post-test are compared to examine the effect of the simulation. At the time of the submission and data analysis, we have recruited 41 participants. The mean age of the participants is between 20 and 21 years old, and with 24 female participants, the male to female ratio is largely 1:1. Most of the participants are college students, with a handful of exception of faculty members and community members. We aim to recruit additional participants to make a total of 59. After participants are greeted into the lab, they are first given a pre-test, asked to interact with the simulation, then asked to finish the post-test. And we will cover each of these sections in more detail. In the pre-test, participants are presented with the question on the computer. Participants are not timed, though they will be reminded of time after 30 minutes. That said, most participants completed the test within 15 minutes. Several types of questions are asked in the pretest, including multiple choice questions as presented here. The participants will be prompted with a scenario that addresses the volume, density, or the shape of an object, and asked to determine if the object will float or sink, and asked to provide a justification for that answer. Another type of question is quantitative or computational questions. Participants are given some parameters and asked to complete some computational problems, such as calculating the volume of water displaced or the amount of buoyancy. This is designed to mimic the questions that typically presented in a traditional classroom setting. After the pretest, participants are introduced to the simulation, and after a few basic instructions about the feature of the simulation, they are allowed to freely explore the simulation. Participants are able to interact with an object submerged or partially submerged in a container. Participants can change different properties of the object and the liquid, including the volume, the density or material, and the shape of the object, as well as the density or material and the volume of the liquid. The screenshot shown here is the screenshot of the last scene, where participants have access to all of the available settings. As mentioned, participants were assigned to one of four conditions with haptic and visual components of the simulation on or off. Participants in the haptic-enabled condition will interact with the simulation through the Falcon device while receiving force feedback as though the participant is holding the object. For instance, attempting to lift a heavy object will result in a downward force feedback, while attempting to press a buoyant object in the liquid will result in an upward force. For participants not in a haptic condition, they will still interact with the simulation through the Falcon, only without force feedback. For participants in the visual condition, force arrows of different magnitudes, directions, and color will be presented around the object to represent different forces. These forces will change in size and direction as the participant interacts with the object accordingly. For participants in the non-visual conditions, no force arrows will be presented. Participants were then given the post-test, which includes all the questions in the pre-test in identical form. This is done with the hope that if participants wish to change their answer after using the simulation, they can. A few additional questions were included, such as a screenshot questions, where participants are asked to compare two screens in the simulation and determine which object is more likely to float. This question serves as a manipulation check and also as a means to further test for understanding. Furthermore, some open-ended questions were also included in the post-test, where participants were asked, for instance, to come up with a simile for a buoyancy. And even though these questions were not scaled quantitatively in the analysis, we have found some interesting responses, and some typical simile for buoyancy are a balloon, a boat, or a seesaw. Finally, for the results. As the graph shows, we have found a significant improvement between the pre-test and post-test only for the haptic and visual component. On the graph, the four conditions are represented by different colors, and while the pre-test is represented by a lighter color, the post-test is the darker color. And as you can see, the only condition that shows a significant improvement between the pre-test and post-test is the far right orange condition, which represents haptic and visual. We have found evidence that supports one of our hypotheses, namely that there is indeed an interaction that yields significant improvement. With additional data, we hope to see a significant effect in the haptic and visual-only conditions, as well as different patterns for different types of questions. The present study does have several limitations. One aspect, of course, is the current small sample size, and we have collected additional data pending analysis. Furthermore, since the sampled population is primarily Davidson College students, this population is arguably varied from the target population in terms of educational opportunities and prior exposure to physics concepts.